Section 5.4, example 18, using the limit comparison test. So for each of the following series, use the limit comparison test to determine whether the series converges or diverges. If the test does not apply, say so. All right, so what we're going to do is look for another function or another summation to where when we take the limit, it makes it a little bit easier. So we don't necessarily have to find another function, either larger or smaller. We just have to find a function. So this differs a little tiny bit from the regular comparison test. What we were looking for was either a function smaller or larger to either to prove that it converges or diverges based on the other one. So here I'm going to let b sub n, a sub n is that one right there that we see up above. I'm going to let b sub n be something easier to make it easier for us to find the limit afterwards. So now we're going to look at the limit as n approaches infinity of a sub n over b sub n. So we have the limit as n approaches infinity of a sub n, 1 over the square root of n plus 1 over 1 over the square root of n. So looking at those two, let's multiply both top and bottom by the square root of n. We end up with the limit as n approaches infinity of the square root of n over the square root of n plus 1. And we could divide both top and bottom by the square root of n plus 1. As in, it looks like an h, as n approaches infinity of 1 over 1 plus 1 over root n. That part goes to 0, and we end up with 1 over 1. And since this is not equal to 0, then we know that both a sub n and b sub n, it's supposed to be n, and b sub n either converge or, so both a sub n and b sub n converge or diverge. So either both of them converge or both of them diverge. So now let's look at the limit as n approaches infinity of b sub n. So n approaches infinity of b sub n. So 1 over the square root of n. So as n gets larger and larger and larger, we end up with 0. So because of this, we could say that both, so since b sub n converges to 0, so does a sub n. So therefore, a sub n also converges. And there we go. So we have that first one done. Let's work on that next one, the second one. Pretty sure we're going to need a little more room. So now looking at b sub n. So we're going to find a function b sub n that's a little easier to integrate. And we're going to use that to help us with the rest of it. All right, so easier for me would just be to remove that plus 1 here. So I'm going to let b sub n equal 2 to the power n over 3 to the power n. So now we're going to take the limit of a sub n over b sub n. So the limit as n approaches infinity of a sub n, 2n plus 1 over 3n over b sub n, 2n, 3n. So multiplying both top and bottom by 3 to the power n gets rid of those. So we end up with the limit as n approaches infinity of 2 to the n plus 1 over 2 to the power n. And if we separate those into two different fractions, we have the limit as n approaches infinity of 1 plus 1 over 2n which this is equal to 1. So this tells us that either both of them converge or both of them diverge. So we're going to look at the sum as n goes from 1 to infinity of 2 over 3 to the power n. And based on this one here, we have a geometric series. The geometric series tells us that because it's less than 1, so based on geometric series, so based on the geometric series, since 2 over 3 is less than 1, the series converges. So B sub n converges. Since B sub n converges, so does A sub n. A sub n also converges. And there we go. That's our solution there. And now based on this, let's move this up here to give us a little bit more room. All right, so that one converges. Let's see. So we're going to find another summation so that when it converges, we're just going to skip this one. So let's do a big skip. You guys won't be tested on this one. All right, so if you have any questions, please feel free to ask. Otherwise, bye.